Okay, this video is going to show you how to calculate the different harmonic frequencies of a string. So let's say we have a string fixed at both ends, and let's say the string is 0.8 meters long. Regardless of how the string is vibrating, that's its length. And we know, so we'll write it over here, the length is 0.8 meters. Let's say it's also tuned to a tension of 20 newtons, which is pretty tight. And let's say that it has a linear density of 2 times 10 to the negative third kilograms per meter, which is a pretty thick string. It's similar to the one we were using in class today. And now let's say we want to know the frequencies of the first 3 harmonics of this string. So let's draw them. We know the fundamental, or the first harmonic, is that one. We know the second harmonic is where it's doing that, going up on one side and down on the other. And we know the third harmonic. Here's the string fixed at both ends again, and in the third harmonic mode, it's vibrating in 3 equal segments like that. Okay, so I know each of my harmonics, I know what they look like, and I can picture them, and I know in all 3 cases the string is 0.8 meters long. Great. So now we want to get the frequencies. We want to get F1, the frequency of the fundamental. We want to get F2, the frequency of the second harmonic. And we want to get F3, the frequency of the third harmonic. Let's start over here, because you know if you have the tension and the linear density, you can calculate the velocity. So let's just start that because we know we're going to need it. So the velocity, if you recall from class, is the square root of the tension, which is 20 newtons. This is for all waves on strings, divided by the linear density, 2 times 10 to the negative third kilograms per meters. And if I do that calculation, you get a nice 100 meters per second for the velocity. That is going to be useful in a little while. I also know that if I want to get frequencies, I'm going to need to use my wave equation. So my wave equation, the most important equation for all waves all the time, is V equals F lambda. So I know if I have the velocity and if I have the wavelength, I can get the frequency. The problem is I don't have the wavelength yet. So let's actually start, come back up here and look at our fundamental. Now, remember from the previous video, but also from class today, you can always figure out the wavelength as long as you know what harmonic it's vibrating in and what the string length is. So for the fundamental, which is a great place to start, you could do it for any of them, but let's do it for the fundamental. We know in all 3 cases the string is 0.8 meters long, and we know that in the fundamental mode that there is exactly 1/2 of a wave on the string at any given time. 1 bump isn't a full wavelength, it's a 1/2 of a wavelength. So we can use our length-wavelength relationship and say, okay, in this mode, L supports a 1/2 of a wavelength. So I'm going to plug that in. I'm just going to do a little, squeeze in a little calculation here. 0.8 meters is a 1/2 of a wavelength in this fundamental mode. And that means the wavelength of that particular wave is going to be 1.6 meters. That's the wavelength for that vibration. I'd have a different answer for F2, for the wavelength of the second harmonic and the wavelength of the third harmonic, but all I'm interested right now is the wavelength of the fundamental. Now I'm going to come back to my wave equation over here, and I'm going to put in everything that I have. So I have 100 meters per second. That's my speed, equals the frequency times the fundamental wavelength, which is 1.6 meters. And if I solve for that, I get the frequency of the fundamental or first harmonic is 62.5 hertz. And that's great. So I've just figured out the fundamental frequency for this string by first here using the velocity, tension, linear density equation, and then coming over here and using the wave equation. And that's always going to be what you do in problems like this. Now, I could go back and I could figure out F2 over here and F3 over here by going through this entire process again, figuring out the new wavelength and coming back to my wave equation. But if you remember, I don't have to do that. I can use the shortcut, which is that I know all higher harmonic frequencies are multiples of the fundamental. I'm going to say that again because it's really important. All higher harmonics are multiples of the fundamental. Multiples of the fundamental frequency. You'll remember that F2, the second harmonic, was shaking twice as fast as the fundamental. So if I know that F1 shakes at a frequency of 62.5 hertz, here we go, 62.5 hertz, then I know that F2 is going to shake twice as fast. Well, twice as fast as 62.5 hertz is 125 hertz. And guess what? F3, which is the frequency of the third harmonic, shaking 3 times as fast as F1. And that is going to be 187.5 hertz. So, to get the higher harmonic frequencies, I don't need to do much. I just need to multiply. I hope that gives you some insight, and I will see you in class later this week.